This is
Morning everyone. So today we have our dear friend, colleague, Professor Shihab Shamma, who has been coming to IST for a long time. And
yeah.
I have a privilege to have my first paper with Shihab from Telluride. We did sound stream segregation, cocktail party problem,
Yeah.
long time back in 2016 and so on. Yeah, so good to have you here. Always.
I'm really happy to be back. It's been many years, and
Before COVID he visited, after COVID he just stopped.
yeah, these damn COVID ruined.
Great to see you. Yeah, okay.
And those of you who are here, you probably don't notice the changes that happen.
Yes.
I mean, maybe you do, but it's amazing. It's just amazing. Those of you who don't know this place, like half of the buildings on this campus are new ones. I don't know what, they were really bored during COVID. So they just build. Beautiful buildings, beautiful stuff. It's incredible. It ruined all my running tracks, but that's okay.
Don't credit COVID. It is centenary. During centenary of this institute, government gave a huge grant, and others gave as huge a grant or more. So
Wow.
they've been getting grants and donations.
It's amazing. I mean, but money aside, how quickly you can build these things.
Yes,
I just couldn't believe it.
that is thanks to central government.
I was looking for monkeys in the trees. I get there, it's the Center for Brain Research. What happened to the monkeys? They're gone. And the animal facility, wow. And the medical school. And, my God.
IDE. Please come to ECE. Behind the PCE is IDE. Unimaginable.
Well, your department, exactly the same.
Yes.
It feels really good to have a home. And I was told that you guys are all hardware people, so I'm supposed to provide some kind of a balance. Although I'm just like you, I was a hardware person 100%, doing integrated circuits and all that stuff. So today's talk demonstrates that it's not too late. You really can get interested in neuroscience, and especially cognitive neuroscience. And the things I'll talk about have not a hint of engineering, barely neuroscience. And it's things that you probably saw some of the people around putting caps over their heads and recording, and you wondered what on earth are they doing here. So this stuff is related to that, like, the projects that Rupesh is doing and all that. So I will talk about things called, I hope by the end of this talk you'll understand the terminology of what I'm talking about. But it's sort of sensory motor, sensory cognitive interactions, and especially those predictive ones. Also, why these things are critical for learning. And it's exactly the same kind of strategies that are used to train all these machine learning stuff and neural networks and all that. Engagement, why do you actually listen to speech and get engaged with it? And of course, even more so, like with music. And how can we study that? And finally, this is like the title of the talk, is really about decoding imagined stuff. So it's not reading your thoughts, don't worry, and we're really still very bad at it, so you can feel safe. But I will try to explain to you how you get from this kind of stuff to this, okay? So I'll go a little bit at a good clip, but so that you don't get bored, but please stop me if there's terminology that I fall into that is not familiar, because I know a lot of the people's backgrounds here are a bit different. So this whole thing started when I had a colleague whose son had epileptic seizures. And they did, that's not him. I wouldn't dare put that here. And they operated on this kid, and they put electrodes in their head to try to figure out where the epileptic seizures are happening and all that. This kid was really a good pianist. He played a lot of Bach and stuff like that. And so he really wanted to do research while he's doing surgery and while he's being treated. And one of the experiments was, when they put electrodes in his head and all that, they played music to him, the music that he's familiar with, and his brain lit up. A lot of activity, you can record all this activity and all that. But the cool part was, when they put him in front of a piano keyboard with the sound turned off completely. And he just moved his finger as if playing that piece. And what happened is, his brain lit up in the same areas as when he was listening to the music, as if my colleagues thought it was like, you would call it, imagine the music that you're playing. So he's just moving his fingers and all that, and the auditory areas, the areas of listening, lit up. So that got me really interested in this whole field, and what is going on? Is this really imagination, or is this some kind of a hardware connection between the fingers and the auditory areas? Because after all, this kid was spending hours every day playing music, moving his fingers, and listening to the sound at the same time. So we decided to do some experiments with some colleagues, but instead of music, it's really hard to get people to have epileptic seizures and be good musicians and all that. So, but everybody is good at talking. So we thought we'll do it with speech. So we had people on the operating table, and they are talking or listening to what they said or miming what they were saying, but moving their mouth but without any sound, just like playing the piano keyboard without any sound. And this, we imagined, is the structure of what's going in their brain. So this gray thing is like supposed to be the brain, and it's obviously a real simplified picture. And since we're interested in auditory and moving your mouth or moving your fingers and all that, so we have two areas, the auditory area and the motor area. And when you move your mouth, when you try to talk and so on, you activate the motor areas in your brain. Those generate sounds from your mouth, which go out in the air and then come back to your ear and go to your auditory area. So that's what this link is about. Or when you're listening to sound, you get activation in the auditory areas. But it was really interesting that we were exploring the connections between the auditory and the motor. Do they talk to each other? And how do they talk to each other? And why, ultimately, really is the question. Why do they talk to each other? So that's what we call disentangling the interactions between the auditory and the motor activities. And as I said, we did experiments with people speaking, people miming, and they're listening to their speech. And this just summarizes the experimental stuff. But this just shows you a picture of how you do these experiments, and there are many other ways of doing it, but the basic idea is you open up somebody's, by the way, you have to be really sick enough to be in a surgical space where there is a doctor and they're treating you, and they open up the skull and they put electrodes or they insert electrodes into the brain, and then you can record, and they sit there in the operating table for quite a while. And so they get bored and they want to do experiments. And so that's the kind of experiments that you do. And there's no pain, there's nothing, and they're kind of interested. And there were, like in this experiments, for example, hundreds of electrodes recording from different places all over the brain. And what we did, the kinds of results that we got from this work, by the way, this picture shows you that some of the electrodes were the green electrodes. That is, these are electrodes on the x-axis. There's 350 or so. And the ones that are activated by just sound, the green colored ones, they're activated during listening. So those, we call them auditory areas, auditory electrodes. And the ones activated by the black are the ones that are activated specifically when there's miming. And the red are during speaking. That is, you're both moving your mouth and you're listening. And there are a lot of detail, obviously, here, but I'll get to some of this. But I just want you to see from an engineering perspective, when we got recordings from 300 and some electrodes, we basically said, okay, we know the input we're putting in, the speech, or we ask them what to say, and so on and so forth. We know the input, we know the output, that's what comes out of the electrodes. Why don't we find what the system is doing between the electrodes and between the speech, or between the signal and the output? And then if we know, we can invert it, we can look at the activity in the brain and decode or reconstruct what the stimulus is to prove to ourselves that we really know what we're doing. And this shows that, in fact, you can do that in miming, you can do it in listening, even in speaking, and so on. So that was really easy. And we could do that very well. You could get all kinds of beautiful analyses. You can spend a lifetime analyzing these kinds of data, looking at listening, miming, speaking, and looking at the type of kernels or impulse responses, or in biology they call them spectrotemporal receptor fields, that take the signal and convert them to electrical activity in the brain. And you see that those kernels are really different between miming and speaking. Like for miming, the activations are even before you begin to receive anything, which makes sense. It's like this is decoding intention to open your mouth and say something. Anyway, so the basic summary of all of that effort after a couple of years of recordings and doing all of these things and all that is that we could see two kinds of interactions between the motor and the auditory areas. When we put sound, we get activity here, and we record in the motor electrodes, we see activations here. We see when people are miming, we see recordings in the auditory areas, just like I showed you. So that shows that there are projections coming from the motor to the auditory, from the auditory to the motor, and of course, the ones that come from the outside. As you speak, it goes to the outside and comes in like I'm listening to myself here. So there are names to these structures, and I'll get to that in a minute. Well, why don't I get to it right now? This pathway, the black pathway, called the predictive pathway, it's also called the decoder. Now, it also has another name called the forward pathway. That's because some of us come from controls, some of us come from computer science, and some of us come from electroengineering, and we use the same but different terminologies for the same kind of process. So when you study linear prediction, predictive pathways are the pathways that basically predict what the signal is going to be at the end. So for example, when you want to talk, the motor areas begin to produce activity to move your mouth, but your brain already knows internally what you're supposed to receive. in the auditory area. So it activates the auditory area with signals that resemble what you expect to receive. And so it's predicting what the auditory signal is supposed to be. So you sit down in front of a piano keyboard and you start playing a piece that you've practiced for a long time. And all of a sudden the keys are all messed up. They're out of tune or something like that. Your brain goes crazy. And the reason is because your brain is predicting a certain sound set to come out. But this sound set that is being activated in the auditory area doesn't match the sounds that are being received from the outside. So there is a big conflict between the input coming from here and the input coming from here. That's really important. We'll get to that in a second. But that's why this is called predictive. What this is the signals going from your auditory system or auditory memory or auditory, and it's telling the motor system what it should do in order to reproduce the auditory signal. So when a pianist sits in front of a keyboard and they have in their mind a certain melody to play, or forget about the great expert pianist and all that stuff. Think about you. When you have a thought in your mind and you want to say something, you're damn good at it. You really can convert the auditory or the thoughts into incredibly complex motor movements on the fly and generate what you wanted to say. That's called the inverse pathway, or the encoder. It encodes the motor activity. This one predicts the auditory activity. This one encodes. By the way, this is called inverse because going from sensory to motor, it's in the opposite direction to this, therefore this is called forward. Terminology forward comes from controls. People who do controls, often one of the controls mechanisms is to actually predict what the control parameters or control commands are supposed to be doing, so that you can very quickly generate the necessary controls to work on the physical plant or the. So this kind of theory has been around forever. In engineering, linear prediction and all of that, in forward control pathways, and therefore this is the inverse. Okay, so I'm going to spend all my time talking about why. Why would the brain do this complicated? Yeah?
Please comment on the motor theory of speech perception. Motor theory of speech perception, which is also a very...
Oh, yeah, that's exactly what it is. So I get attacked every time by my colleagues. It's not quite, and so, okay, what the question is about is people always thought, maybe you really only understand me, that is, understand the speech that I'm giving you, is because your brain quickly, as the sound comes in, inverts it to the motor commands that correspond to what you would have done in order to reproduce it. And if these motor commands, these motor commands are like the features of the speech. So you don't do spectrograms, you don't do any of that stuff, you don't have to. You just go into the motor domain and represent the speech in the motor domain. That's called the motor theory of speech. Yeah.
Isn't it used for imitation learning?
Isn't
it used for imitation learning?
I'm going to talk about this. Yeah. This is used in imitation learning. Yeah. Okay, so the question is, why and how do we, well, first of all, so here I just redrew exactly the picture you had, but I redrew it by opening up. You remember there was an inverse pathway and a forward pathway. So I basically took the auditory cortex and took the inverse pathway here and just flipped it here. So this is the same as the thing on the right there. There's the inverse pathway, the green one, going into the motor, and there's the motor having two. The the outside, that's the physical plant or what have you, and this is the forward predictor or the decoder. So decoder, encoder, inverse, forward, it's the same thing. All these terminologies are the same. Yeah?
Where exactly the motor planning happens?
Here.
In the motor cortex?
Well,
Planning?
who knows? I can say anything. But, okay, with everything here, these are the places we record at in the motor cortex and the auditory cortex. There are also areas which store the speech, the thoughts, the music, all of that stuff. These are memory areas. Where are they? They're all over the place. Yeah. So motor plans, for example, the basal ganglia or the thalamocortical loops or God knows where. Yeah, there are a lot of different places. Okay. But let me just give you a feel for why, for example, how the decoder is useful. So you remember I told you if you come to play a piano and you start moving and then the wrong notes come out and all that stuff and you don't like it, what happens the first time you come to look at the keyboard, or since we have here mouth and ear, imagine you're a baby and you're trying to learn how to talk. Well, the first thing you need to do is to learn how to control your vocal tract so that you can produce this varieties of sounds and all that stuff. And the same thing with the piano keyboard. Well, what you do, and if you notice your baby or if you notice somebody practicing on a piano and all that stuff, you just do randomly, move your fingers around the keyboard and all that stuff, and what you're doing is you're beginning to associate where you press with the sounds that you're listening to. So you're creating a link between the auditory and the motor. And the exactly same thing is happening with the baby trying to practice to talk. They just say anything, but they're listening to what they're saying. And I don't mean words. Bag, bag, ga, ji, pu, ga, all of that stuff. What they're doing is they associating the musculature and the movements and the sensations in their mouth to the sounds that they're listening to. And how they begin to learn is completely unconscious, completely implicit, it's without instruction, it's just random gibberish. But they learn when they do that, because when they start producing random motor activity, whether it's hitting the keyboard or producing sound, their forward predictor is generating some activity in the brain, but it's not trained correctly because it doesn't know what to expect. Once it knows what to expect, it means it knows how to control its vocal tract, for example. But initially, it's producing garbage here. And on this side, whatever the motor activity commands were, they're producing sound that goes into the auditory. So this arrow and this arrow don't agree, just like when you're moving your hands on the piano and it's producing unexpected sounds. This disagreement between those two is what we call the error signal. And this error signal automatically begins to be reduced. And how? By basically training this back prop or whatever you want to prefer your favorite learning thing. It basically tries to update the mapping from the motor to the auditory in such a way as to make this mapping reproduce whatever comes from here. Okay? So this happens completely implicitly, completely without any training or anything. Yeah?
So is this distinct from the inverse pathway?
From what?
From the inverse pathway?
Completely distinct. Inverse process is right here. Inverse process requires a teacher, requires training, requires skill. Absolutely. Yeah, so anybody can learn to hit the piano and even expect the sounds. But you tell them, can you play me please a melody? Or play something? And you really need to train. I mean, most of us anyway. And so that's configuring the inverse pathway. I'm going to get to this in a second. So we learned then how to do this pathway. So this pathway, let's say it got trained after a few months to predict exactly what is coming out of your motor system, so you know the control. Yeah?
Is the efference copy from the motor activity playing any role in this? Is it
The efferent copy,
of the motor plans or of the motor commands?
so the motor plan is what's generating this. Initially, it can be anything. You just spontaneously. But, just like the question asked a minute ago, if I give you a melody and I ask you to play, you need to know how to create that motor set that generates the beautiful music. And therefore, you need to map the sound into motor. Motor can be talking, for example. So I ask you, somebody asked me about, about repeat and repeating and learning to repeat and all that stuff. You ask somebody, please repeat after me. And you ask them to say after you something. To do that, it requires you know. So you've heard it. It's in your head what the auditory signal is, but you need to map it to the appropriate commands that move your mouth in such a way as to generate the sound that you expect to get. So there is an error between the intended sound and the produced sound. That's that error one. That is the one that is difficult and requires a lot of training. Nobody, and many people spend a whole lifetime practicing all the time trying to get their accent right. And it's not hopeless, but it's difficult. And that is basically because in order to train this, you need to know what the correct motor commands are. Well, how do you know what the correct motor commands are? Well, you have to get this error signal. But to get this error signal, what do you do with it? You need to update your motor commands. Well, how do you get to the motor commands? And that is the magic of this forward pathway. Without this pathway, you have an error signal measured, but then you don't know how to neurally change this. With this pathway available, you can back propagate through it to the motor system. So you know what the error here is. That's E1. You back propagate here, and now you can update this pathway. So without this pathway, you cannot learn. There's just no connection. And this is really a beautiful, it simplifies things and makes the nervous system be able to tweak, constantly tweak as you train, what the command should be. And yeah.
Please comment on, it's harder to imitate prosody than phonetics. Any comments on that?
To repeat on the phonetics?
Yeah. No. It's harder to imitate prosody, speech, like the intention.
Yeah. Well, that's basically because to speak well, you need to go from so there are many things about learning skills and all that stuff. Let's say you are, if Elisabetta tells me in Italian, say this, and she says it too fast. Well, guess what? I'm not going to have the appropriate auditory memory to take what she said and store it and recreate it with my mouth. And so that's one problem. You have to really be able to quickly encapsulate the auditory, but then even if you do, you need to have this pathway trained. To train this pathway, you have to go through all the way back. Now, if your mouth has been speaking English all your life, this pathway is back propagating English errors. And to try to get Italian here. And that's not what you did. End up basically speaking Italian with an English accent. So, it's not so bad. It's not as beautiful, but that's okay. So by the way, people who study cognition and all of that stuff and try to study this process in real people in the lab and all that, they do experiments where here they do tricks called altered auditory feedback. It's exactly what I told you about playing the piano and suddenly you change the keys on the piano. And you get surprised. And the classic one is when they make people speak and then they change the pitch of the voice. They make them wear headphones and then they suddenly change the pitch and people go, what? Now this reaction, the so-called what? It's called surprise. It's a technical term. Don't think of it as literally a surprise. And it's simply referring to the error signals that you get when your expectation is not matched by your production. Okay? So I'm going to talk a lot about that. But as I hope by now you realize that expectations, that these errors are critical in order for you to know that you're not doing the right thing and you need to learn. So they're used in the learning process. The errors, both the errors here and the errors for this one. So those surprise are exactly what's needed in order to learn all these pathways. I cannot hear you much.
I just wonder,
Yeah, thank you.
In case of a child learning,
Child learning.
what happens to that forward reference path with which you generate?
This one or that one?
Yeah, in the decoder forward.
Well, it gets updated all the time because they're just saying, and they start basically appreciating what their mouth can produce with their, when they hear it. So this is the pathway that they listen to themselves, and this pathway is what they expect that they should hear. But it's all happening internally. So there is a mismatch, there is an error, there is a surprise, but it's simply used in order to update this pathway so that the motor system predicts the correct sound. So they know when they move their mouth and they curve their lips and they go like that, what they expect to get. They learn their pitch, they learn all of that stuff. Yeah.
Well, so one of the things that kind of killed behavioralism to an extent, right, was the idea that there are these experiments where, for the first time ever, your mouth will be in a position that it's never been in, and with no learning whatsoever, you're able to kind of adjust and make the sound that you want to be able to do. So it couldn't be a stimulus response.
Yeah.
How would this sort of account for that?
Well, that's basically that.
Yeah. You're just saying that's robust enough to be able to handle.
Absolutely.
Yeah, okay.
Yeah, you know your mouth hopefully after a few years of moving your mouth. Yes, you're right. Yes.
Yeah, so someone born deaf, how can they learn to speak meaningful things?
It's very difficult if they're deaf from before learning to speak.
Yes.
Yeah, that's why deaf people don't speak well. It's because they don't have a feedback. In fact, even if they become deaf after they learn to speak, like at the age of 10, they suddenly come completely deaf. They start getting feedback correctly, and so this system begins to deteriorate, and so it's not maintained. And so their ability to produce the correct sounds diminishes, and you can tell because you can hear it. And, yeah.
Maybe one more on that point.
Yeah.
Like there's people whose parents are deaf.
Yeah.
And then because of that developmental time, they're not able to fully form words. It's a lot harder for them to form words later on. Is that because there's like a time period for the encoder it works really well?
Yeah.
Okay.
Yeah. So, I mean, the encoder is learning skills, and that skill requires instruction, requires a teacher, requires all kinds of things like that. And that's the problem with this pathway. Yeah.
The old age hard of hearing does not affect the speaking.
Does not affect the what?
Speaking.
Hard of hearing does not affect the... Hard of hearing is not the same as deaf. I mean, you can get some feedback, especially hard of hearing happens gradually. Just like, those buildings on IISc, you remember I told you, you don't even notice them. Some of you probably don't even know what I'm talking about. But these things are real. And hard of hearing, actually one of the worst problems about hearing issues and all that is that people can't tell that they become hard of hearing. It happens so gradually. And they just refuse, I mean, in addition to refusing to acknowledge it, they can't really tell. They keep going out to restaurants. Why are restaurants becoming noisier? They've always been noisy. So it's that thing. When am I supposed to stop? I just like...
10:30.
Huh?
10:30.
Okay. So I'll get to something. Okay. So I told you about decoders learned implicitly without instruction and all of that stuff, and this is learned with and by the way, everything I told you can be made and I'm just trying to tell you that the forward pathway plays a huge role in providing a backprop pathway to train the inverse. If you don't know, if you don't have a control, if you don't have a correct forward pathway, you're not going to be able to do the inverse. Because how are you supposed to learn to speak some thoughts and all that stuff if you don't know how to use your mouth to? And so you need both pathways, and especially the forward pathway to backprop through.
Isn't backprop biologically not plausible?
Could the backprop do what?
No, isn't backprop biologically not plausible?
Oh, I'm not going to... there are many other options, even recurrent pathways and all kinds of stuff, but the basic idea is that you need to learn how to use it. You need to have the motor plant correctly controlled before you use it to do anything, intelligent. That's all. So yeah, you're right. Some people don't like the backprop. They think it's not biological. Maybe. It's not established, but it's not the only option. Yeah. Okay. So, by the way, just to say a couple of words about doing this, translating this to building a system or building, like for example, imagine you want to train a car to go drive, and basically you have cameras or you have sound or you have whatever sensory systems you have, and this is the car, and you want to send commands to the car to tell it to move left and right and all that based on the sensory information. So what you want to do is you want to train it in order to go left or right depending on where either the visual signal or the auditory signal, whatever happens here. So everything I told you here, the decoder and the encoder are just basically backprop neural networks. Okay, and this is your motor system. So this is actually the speech synthesizer called the World. I think it's called the World. And here the motor system controls the intensity of the muscle, tension in the muscles of your larynx to tell you the pitch of the sound, so you can modulate and not be a really boring speaker what doesn't change your pitch at all and all that stuff. And here you need to move your lips and what have you, and also to generate aspirated sounds or voiced and so on. So all these are the motor commands to shape your mouth and to shape the signal that comes out of your mouth. And you can train this neural network to do this all spontaneously and all of that. And here is the inverse decoder. So we use this to train vocal tracks. We used it. By the way, the nice thing about this is that I really don't need to know the details of the physical plant and all that stuff. Whatever it produces, we come with different mouths and all that stuff. If all of humans learn with one mouth, it will be a problem. However, if one day you wake up in the morning and your mouth is different, or your ear is different, you're in trouble. Because you've learned basically to do these mappings with the correct vocal tract and the... Okay, let me just move fast. This is just examples. You can do all of this stuff computationally. And we'd like to study it with animals, but animals don't speak and they don't play music, so it's kind of annoying. But we trained ferrets to anybody heard of the musical instrument called the theremin? Yeah? So this is an instrument where, since most of you have not heard of it, you create an electromagnetic field, and you're in front of this electromagnetic field, and you move your hand, that disturbs the electromagnetic field, and then what you have is an amplifier, as a receiver, antenna with a receiver and an amplifier, which takes the modulations in the electromagnetic field and generates this absolutely gorgeous sound. And some people are really good at it. And you can play music by just moving your hands and stuff like that, and change the pitch and change the vibrato and do all kinds of stuff. So we say we put ferrets, and we had the ferrets move their head to the left or right, and when they do that, there is a sound that is produced. A pitch, for example, of a tone changes from high to low as they move their head. Either by, you can do it with an electromagnetic field, or just put a camera, see where their nose is pointing, and then give the feedback to the sound. So that's like basically the bird experiments with Richard, and while the animals are doing that, we can actually record in their brain, in the motor areas, in the auditory areas, how they begin to learn the map. And it's really remarkable. It takes them few minutes to establish a map between where their head is and what the sound produced is. And we can also record in humans playing a piano, but what we do is we take the piano keyboard, we make it randomly shuffled, and they come and they start doing this, and of course generating random notes and all that stuff. And within few seconds, humans show evidence in their head of connecting that decoder pathway beginning to form and mapping the auditory to the motor. They have no idea they're doing that. Yeah?
Where is the map? Is it in the auditory cortex, in the motor cortex?
Well, it shows up in the auditory areas. It probably shows up in the motor too. So because it's all about interactions. So it's the auditory feeding to the motor and the motor feeding to the auditory and back and forth. That's why all of this has been called mirror networks, because they mirror each other. And so, yeah, it's everywhere. But you really can see it. And yeah.
Is there a task involved for the ferret?
Yeah, not yet. These ferrets, they initially, only work with one map so we can actually see what the evidence of the maps and all that stuff. Then we switch the map all of a sudden, and then you can tell right there they react. And the same way people sometimes react, but only if it's organized enough that they can detect it. But you can do a task easily with them by having them, for example, giving them a tone and give them water if they move their head in the correct direction to go to that. That would be the inverse pathway. Yeah. So they're being trained to do that now. Yeah.
Is there any difference in terms of if you change this map all of a sudden, or if you change it incrementally over sort of some time? Say the example of the piano.
Well, if you change it incrementally, the error is small, so you get the updates done on the fly and gradually as it happens. If you do it suddenly, well, the error is big and you notice it. So you can become conscious of it. Yeah. Okay, let me get. So everything I talked about is with the three pathways all integrated, all available. The inverse pathway, the forward pathway, and the feedback external action pathway. You can call it. By the way, everything I'm talking about, call it auditory, but it's involved in vision, it's involved in dancing, it's involved in just about anything you do that requires you sensing and knowing how to act motor-wise in reaction to that. So all of these have the same principle and all that. But now imagine we have the deaf system, okay? How good, I apologize. I shouldn't call it the deaf system, but you don't have, imagine you don't have this pathway available, that feedback. Okay? So when you say you don't have this feedback, when do you do this? Or when do you actually not use this? Suppose you're sitting at home and you really want to enjoy listening to some music. Okay? You're not playing music. You're not moving anything. So this is really about listening to the sound and enjoying the music that is coming out, that is getting into your ear, to listening system. So there's no motor issue generating sound and being compared to this and all that. Believe it or not, the same pathways and all that stuff are used in a big way for you to enjoy the music. So let me explain how that comes about so that you see how, if you remove that, that's the system you end up with, okay? And now I'm talking not about the motor system, but this beige part of the brain is where we talked about where is the memory of the language or the music. This is your memory store for music or for language or whatever it is, here, okay? And you got this system and I removed that. So now, let's see what happens. When you listen to music, it's getting into your auditory system. When you listen, as you listen to music, often, suppose you know this music, and it's the music you've liked before, you've learned it, you became familiar with it. What happens is, as you're listening, the sound that goes into the auditory system goes into your auditory memory. Your auditory memory is generating a prediction of what this music is supposed to be. You notice that when you're listening to music, you know, you're sort of singing with it, if you will, or I'm just giving you an informal kind of language to do that. And if this singer is lousy, or if the radio is lousy, or whatever it is, there's going to be a big error between what you're listening to and between what your memory tells your expectation. That difference between the expected music and the music you're listening to, the delta E, is exactly the kind of error that is used to update your memory store. And that can happen through the inverse pathway and also through the, so let me, so, all the time, when you're listening to anything, whether it's language or listening to music, you're constantly expecting. It's just like the large language models. They're constantly predicting what the next word is. That's exactly what this is doing. And when there is an error between what's expected and what's being received, you know that either your system is not correctly remembering things and knowing how to predict, or your predictor is not correct. So you need to update these. And in the end, you acquire the new music or the new, in such a way as your expectations match what you're listening to. So that is what's referred to as the role of, to do the interpretation, you need the prediction, and you need to learn. And if there's no error, everything is exactly what you'd expect, this is really boring. So boredom is when you're not learning anything new. Okay, that's what this is saying. You need the deviance, the surprise, the error, in order to acquire new knowledge and all that. Because new knowledge means your expectations were not correct, and now you're going to update your knowledge in order to have the correct expectations. We do this all the time in the lab. Maybe Rupesh can show you some experiments to show you. You can play music that you've never heard, or play music that has something that is unexpected or something, and you look in the activity coming out of your brain, and you see these extra bumps that reflect the errors. And as you listen, and the music becomes familiar and all that stuff, these bumps disappear. And that is what's going on all the time. And in fact, without these bumps, when I see these bumps, I know you don't know this music. So I can assess your internal knowledge by detecting these bumps. And how do we detect these bumps? We detect them by, basically, we take the EEG signal and we say, should we take the bumps into account in order to predict the EEG signal? And if we do, and we discover that we can do a better prediction of the EEG signal, then we know that we have detected these bumps, and we can say all these things. So the bottom line, what I'm trying to tell you is we can use these bumps, I call them bumps, but call them surprise signals, call them whatever, errors, whatever. We can use them to assess what you know, how good you are at, for example, I can take people who've never spoken English or people who speak really native English and let them just listen to English. And the ones who are native speakers have hardly any of these surprise bumps and all that, and the ones who don't have good mastery of the language and all that stuff, they have a lot more, and you can actually quantify and predict their skill from that. And same with music and so on. If you have somebody who is coming from a different musical culture, either, like, for example, in this room, some of you listen to certain kind of music that the other person never hears, and they prefer a different kind of music. You put them together, and you can tell what the musical corpus in your head is by just looking at the... Now, the way we do this normally is we do a lot of mathematical models. So, for example, we can make language models, and I use the language model to predict what the expectations are supposed to be. And, or music, the same thing. I can take, for example, you give me a piece of music, and I can, let's say it's Western piece of music. There are models out there for Western music, and you get notes, and the model tells you what the next note is supposed to be. Now, if your brain is showing a big surprise, it means the Western music model is not your model. You have some other model. So I change it to make it fit what I think your model is, and if the surprise goes, then it means that, yes, that is your model. So we can study the enculturation, how you get, when you get exposed to different types of aspects of culture, how do you internalize them? How do you store them? How do you compare them across, and so on and so forth? Okay, in the interest of, yeah, this is basically telling you about the EEG in the lab, and you can give the sound, you can record with this red cap what the electrical signals coming out of your brain, and then we can measure, we can make a linear model of what sound should produce here, and if my prediction is wrong, then I adjust the system, adjust the model to capture it better. Okay, so let me go to the final part. This the next slides is all about music, the same story. These are the models of music. We did a study, for example, with Chinese listeners and Western listeners. Western listeners listen to Chinese music versus, and also Chinese, it succeeded beautifully for the Westerners listening to Chinese music. There were surprise signals everywhere and errors and all that stuff, and after a while, when they heard Bach with a Chinese instrument, they could predict it, and it was perfect and all that stuff. So you could see the evolution of culture and all that. We couldn't get the other experiment done right because everybody at NYU Shanghai listens to Western music all the time anyway. And so we couldn't find good subjects that only heard Chinese music. And so we can test the... Okay, so I apologize, I'm just moving through these slides. Let me end with imagination. How does imagination work? Can I get in 5 minutes? Okay. So imagination is when I don't have any stimulus to give you, and I ask you to imagine the audio, or imagine speaking, or imagine this, or imagine that, yeah, depending on the sensory system. So I'm going to kill all of this, okay? So the system becomes real simple. From your imaginary story, you imagine the music, and now, those of you who probably have had this experience where you imagine music in your head, playing in your head, this is real. And we did experiments where we got these really great musicians, and they played certain pieces of music, Bach chorales is called, and we asked them to listen to it and then to imagine it. And then we recorded the electrical signals in their head while they're doing both. And what we discovered is that when they imagined, when they listened to the music, it's what you would expect. The music goes into their head and generates certain pattern of activity, which we are now familiar with. But when we asked them to imagine the music, it went through this predictive pathway because they couldn't help it. When they imagine, they're basically generating music in their head, generated through this forward pathway. When we recorded in their head while they were imagining it, we got just like those signals I started with in the very first 2 slides or something. But now we're doing it with EEG. So I'm just, these are the recordings of so these imagining versus listening and all that. And these are the, oops. What we discovered is that when you're listening, the signals you're generating are inverted compared to when you're expecting, predicting. So basically the predictive signal is wants to compare to what you're listening to. But if there's nothing to listen to, then the comparing signal is inverted. And so you get the inverted path, the inverted signals in your brain when you're imagining the audio, and that's what this is telling you. So when now why this is really cool is because if I ask you to imagine now, let me just say, I mean obviously this is with a lot of hand waving, but basically if I ask you to imagine something, something that I know, like imagine this piece of music in your head, if I record first what's happening in your brain when you're listening to that music, I should expect that when you imagine it will be the inverse of that. It's actually inverse and slightly delayed. Now, why that's cool is because we have a way of capturing what the imagined signal should look like from the listening. And that's basically the key to trying to decode imagined speech and imagined music. Why? For the following reason. Doing the experiments to record your imagined activity, you can do it with a few professional musicians, and they are dedicated and motivated and all of that stuff. It works. You tell them, please start here, please follow the metronome, please X, Y, and Z. But grabbing somebody from the street and have them imagine, it's a waste of time. You don't know if they're really imagining. They could be just want to get paid and leave. How do I know?
But maybe they're not skilled at it.
Maybe what?
They are not skilled at it. I wouldn't be able to do it.
Well, I won't pay you. But I wouldn't know. You fool me.
But what if you make me imagine words? I could be good at that. But
I know, but yeah, but you know, we have people who fall asleep while they're recording, and we think, oh, they're thinking about imagining and all that stuff, and then it's just like waste of money.
Isn't it because the musicians activate the motor cortex because they imagine actually moving the muscles rather than imagining the music itself?
Well, even if you imagine moving the muscles, you're not moving the muscles. So I wouldn't know if you're imagining it.
But only musicians have this mapping between the sound and the muscles.
Oh, yeah.
The person from the street.
Yeah. But I can ask people to imagine speaking. Everybody knows how to talk. So. But the problem is, I don't have an objective way of triggering at the correct place, knowing that they're listening to my instructions, really doing what I'm telling them. You cannot generate a data set. If you have the best, biggest data centers, it generates 3 subjects. You can't train a decoder based on few subjects. Yeah.
Is it multiplex, like can we listen and imagine at the same time, or talk and imagine at the same time?
You're doing that all the time. Yeah, that's what I did with the listening to the music. You were listening and you were sending expectations. That's like imagining. So yes, you are imagining all the time when you're listening, and you're also imagining all the time when you're speaking and playing music and all that stuff. That's what the predictive pathway does. But when you're simply imagining with no motor, no listening, no nothing, by the way, there are people who have this disease where they cannot move any muscles. And the idea is to try to get to their mind and decode their mind. That sort of thing.
But isn't it sequential, because we have to constantly focus on listening to someone else or
Well, you have it already in your memory store. So when I ask you to imagine a piece of music, I'm assuming you know it. And you stored it from before. You're right. You listen to it all the time and all that stuff, you played it, and you have it stored in your head. But when I ask you to imagine it, I want you to go to your memory store, get it out, and at time 0, produce it. And don't produce it too fast, not too slow, and please produce it at least, so that you can get your $20 for the hour and stuff. Anyway, yeah.
Magic filter.
Yeah. So,
That's just enough.
I don't want Shitan to get up here and push me off the stage. So I'll take these are questions.
Yeah, one quick question. So sometimes when we're, not sometimes, most of the time when we're reading something, we're thinking it out loud, right? And I'm assuming from this one that the same areas in the auditory part would get activated. So let's say I'm deaf from my birth, and I don't learn to speak, but I learn to read. Then would the same areas would get activated when I'm reading?
Probably not.
Okay.
So reading is coming from the visual areas and all that stuff, and you know, a lot of people also can. I mean, there's nothing. Okay, there's no fundamental link between sound and speech and language, and because people can communicate with sign language, for example, and they have as much of a grammar as exactly as when they're speaking. It's a true language. So language is a different faculty from auditory and all of that stuff. Yeah. Yeah. We are born, humans have this innate need and ability to have a language. As far as we know, we're the only ones. Yeah. Yes, please.
Have you seen any work done looking at people when they're coding or programming? Because that feels like a similar kind of sequence-based.
So I had students working with another faculty in the department, working on people doing math.
Okay.
And you get the same kinds of things. And when there is a 1 + 2 = 4, they go crazy and their brain doesn't expect that, and so on and so forth. And that's published, and people have done a lot of this kind of math and all that. Yeah, so coding, I suspect, is the same. That's why the language models can do well coding, and yeah. Yeah.